Well, welcome. In this screencast, we take a look at reflections. The reflection is probably one of the most basic things we can talk about, and it piggybacks on the idea of symmetry that we're already acquainted with. So we take some shape, like so, and we have some line, like so, and we decide that we are going to reflect this triangle ABC over this line L. What does that mean? The point A is some distance away from the line. We measure that distance along a perpendicular. And then we decide that we want to go that exact same distance in the other direction away from the line, like so, and the image point is usually called by a prime. A prime is the image of A. Then we do the same thing for B and C. B is some distance from the line. We measure that distance along the perpendicular. Then we go an equal distance away from the mirror, and we have B prime. C is a certain distance from the mirror. We measure that distance along the perpendicular, and then we go an equal distance into the mirrorverse, and we have C prime. And so the image triangle looks like this. This is how reflections are done in the geometry that we teach to small people. In the geometry that we teach to small people, to children in elementary schools, reflections are done by measuring to the mirror and through the mirror, to the mirror and through the mirror, to the mirror and through the mirror. Each point and its image are equal distances from the mirror. Each point and its image equal distances from the mirror. Each point and its image equal distances from the mirror. What are the effects? Well, we know that line segment AB is congruent to line segment A prime, B prime. Like distances are preserved. Similarly, BC and B prime, C prime, AC and A prime, C prime. We also know that all the angles are preserved. Angle ACB and angle A prime, C prime, B prime are congruent. Angles do not change after a reflection because the shape is preserved after the reflection. Whatever the triangle looked like before, it looks like after, with one small exception. And that is this: orientation is not preserved. Well, what does that mean? When we name triangle ABC on the original shape, it's named in a counterclockwise way. We call ABC, and when we see ABC, we go counterclockwise to say them. But in the image figure, to go ABC, we go clockwise to name them. And so orientation is not preserved under reflections. Orientation was preserved for translations, and it was preserved for rotations, but it is not preserved for reflections. The orientation changes from one figure to its image. Okay? So if you had some figure and you knew its image, maybe it looked like that, and you wanted to find where the reflection line was, how would we do that? Well, the reflection line, we imagine that it's sort of like right through here, don't we? The reflection line has to be equally distant from any point and its image point. Well, how do we find that? Well, we connect those with a segment, and we find the perpendicular bisector of this segment, which means you drag out your compass and you do the fishy thing, and you get some line looks like this, and this line is the line of reflection. And if it really is the line of reflection for this triangle and its image, then it will also be the perpendicular bisector of that segment, and it will also be the perpendicular bisector of that segment. And it certainly appears that that blue line is the perpendicular bisector of the red segment, the green segment, and the blue segment. Okay? On the coordinate plane. How does this happen on the coordinate plane? So let's imagine here's a triangle ABC. A is 1, 1. B is 2, 3, 4, 5, 1. And C is 5, 3. We can do reflections. We can reflect over the x-axis. And you can imagine what the reflection looks like, what the image looks like. It is worth examining what happens to the coordinates of A and B and C as they become A prime, B prime, and C prime. We can reflect over the y-axis. It is worth figuring out. It is worth pausing the video to figure out. What happens if we reflect over the y-axis? What happens to the coordinates of A, to the coordinates of B, to the coordinates of C as we reflect over the y-axis? But we could do more. We could take this, let's take this triangle. This is A at 1, 1. Let's do B up here at 1, 4. And C over here at 2, 3. We could take this triangle and we could reflect it over y equals x. We could reflect it over y equals x. We could decide that we want to, well, that's on the mirror, so that is A prime, but we could measure perpendicularly to the mirror, perpendicularly through the mirror equal distance. We could measure perpendicularly to the mirror, and then perpendicularly to the mirror and perpendicularly through the mirror equal distance. And it is worth examining what happens to those coordinates as we go over the line y equals x. That's worth doing. But we could take that triangle ABC and we could reflect it over a line that's vertical but not an axis, like maybe x equals -2. And we could say, you know what? I can measure to the mirror, through the mirror, make a dot, to the mirror, through the mirror, make a dot, to the mirror, through the mirror, make a dot. And you could figure out what the coordinates of those points are. And in all cases, all the segment lengths were preserved. Every image is congruent to its pre-image. Every image is congruent to its pre-image. All the angles stay the same. All the segment lengths stay the same. But orientation is in every case reversed. ABC is clockwise here, but its image is counterclockwise. Its image is counterclockwise. Even on this slide over here, ABC was counterclockwise here, but it's clockwise for its images. These are properties you want to be able to play with. You want to be able to, on a coordinate grid or off a coordinate grid, know what reflections do and how we do them. I hope this is helpful. Second screencast for this lesson is on glide reflections, which takes this lesson and combines it with another.